Hello, young chemists. Have you ever wondered why a molecule of water always contains exactly two hydrogen atoms and one oxygen atom? Or why sodium always combines with chlorine to form sodium chloride? Well, the answer lies in the concept of valency, the combining capacity of elements. Definition: valency is the number of electrons an atom can lose, gain, or share to attain a stable electronic configuration, usually that of a noble gas. It tells us how many chemical bonds an atom can form with other atoms. For example, carbon has a valency of 4, which means one carbon atom can form 4 covalent bonds, as seen in compounds like methane. Valency is the language through which elements build molecules, from water and carbon dioxide to glucose and proteins. Let's now explore how elements are categorized based on their valency, starting with monovalent elements. Monovalent elements have a valency of 1. They can either lose one electron to form a positive ion or gain one electron to form a negative ion. Examples of positive monovalent ions, also called monovalent cations. Potassium ion, symbol K superscript plus. Sodium ion, symbol Na superscript plus. Lithium ion, symbol Li superscript plus. Hydrogen ion, symbol H superscript plus. Ammonium ion, symbol N8 subscript 4 superscript plus. Now let's see monovalent negative ions, also known as monovalent anions. Chloride ion, symbol Cl superscript minus. Hydroxide ion, symbol OH superscript minus. Nitrate ion, symbol NO subscript 3 superscript minus. Iodide ion, symbol I superscript minus. Bromide ion, symbol Br superscript minus. Example reaction: sodium ion, Na superscript plus, reacts with chloride ion, Cl superscript minus, to form sodium chloride, NaCl. Another one, hydrogen ion, H superscript plus, combines with hydroxide ion, OH superscript minus, to form water, H2O. Valency 1 elements form the simplest binary compounds, but they're everywhere around us. Let's move on to divalent elements with a valency of 2. These elements can lose 2 electrons to form divalent cations or gain 2 electrons to form divalent anions. Examples of divalent positive ions include calcium ion, symbol Ca superscript 2 plus. Magnesium ion, symbol Mg superscript 2 plus. Zinc ion, symbol Zn superscript 2 plus. Barium ion, symbol Ba superscript 2 plus. Iron in ferrous state, symbol Fe superscript 2 plus. Copper in cupric state, symbol Cu superscript 2 plus. Examples of divalent negative ions include sulfate ion, symbol So subscript 4 superscript 2 minus. Carbonate ion, symbol Co subscript 3 superscript 2 minus. Oxide ion, symbol O superscript 2 minus. Sulfide ion, symbol S superscript 2 minus. Example reaction: calcium ion, Ca superscript 2 plus, combines with two chloride ions, each Cl superscript minus, to form calcium chloride, CaCl2. These elements are crucial in building salts, bones, shells, and even chalk. Trivalent elements have a valency of 3, they can form 3 bonds. Examples of trivalent cations include aluminum ion, symbol Al superscript 3 plus. Chromium ion, symbol Cr superscript 3 plus. Iron in ferric state, symbol Fe superscript 3 plus. Gold in auric state, symbol Au superscript 3 plus. Examples of trivalent anions include phosphate ion, symbol Po subscript 4 superscript 3 minus. Nitride ion, symbol N superscript 3 minus. Example reaction: aluminum ion, Al superscript 3 plus, combines with 3 hydroxide ions, O8 superscript minus to form aluminum hydroxide. Trivalent elements often participate in complex formation and are key components of industrial catalysts and biological cofactors like iron in hemoglobin. Now we arrive at tetravalent elements, those with a valency of 4. They can form 4 chemical bonds, and the star of this category is carbon. Examples of tetravalent elements include carbon, valency 4, no charge, forms molecules like methane, CH subscript 4, spelled capital C, capital H, and the number 4 as subscript. Carbon dioxide, CO subscript 2, spelled capital C, capital O, subscript 2. Lead in plumbic form, symbol Pb superscript 4 plus. Tin in stannic form, symbol Sn superscript 4 plus. Platinum, symbol Pt superscript 4 plus. Example reaction: 1 carbon atom, valency 4, bonds with 4 hydrogen atoms, each with valency 1, to form methane, CH subscript 4. These tetravalent elements play a huge role in organic chemistry, metallurgy, and the electronics industry. Now let's talk about something fascinating: variable valency. Some elements can show more than one valency. This happens especially among transition metals, where electrons from inner shells participate in bonding. Examples: iron, Fe, can be ferrous ion, Fe superscript 2 plus. Ferric ion, Fe superscript 3 plus. Copper, Cu, can be cuprous ion, Cu superscript plus. Cupric ion, Cu superscript 2 plus. Mercury, Hg, shows mercurous ion, Hg subscript to superscript 2 plus. Mercuric ion, Hg superscript 2 plus. Gold shows Aurous ion, Au superscript plus. Auric ion, Au superscript 3 plus. Example reaction: iron in ferric state, Fe superscript 3 plus, forms iron chloride, FeCl3, when it combines with 3 chloride ions. This variable valency allows these elements to form multiple compounds, each with different colors, reactivities, and applications, from medicines to pigments and batteries. Let's wrap up today's lesson with a quick revision. We explored how valency governs the number of chemical bonds an element can form. We saw monovalent ions like Na superscript plus and Cl superscript minus. Divalent ions like Ca superscript 2 plus and So subscript 4 superscript 2 minus. Trivalent ions like Al superscript 3 plus and Po subscript 4 superscript 3 minus. Tetravalent atoms like carbon in CH subscript 4 and CO subscript 2, and finally elements with variable valency like Fe superscript 2 plus and Fe superscript 3 plus. This chart of valencies helps us write correct chemical formulas and understand the structure of molecules. So next time you see NaCl or CaCO subscript 3, you'll know exactly how those atoms got together. I hope this class helped you master the concept of valency. In the next video, we discuss writing the formula of chemical compounds. Until then, keep observing chemistry in the world around you. From rusting iron to fizzing soda, it's all about how atoms combine.